This is APAB Calc. We are doing the second video in section 1.5, which is limits as x approaches plus or minus infinity, which we can sometimes call, we can always call end behavior. So sometimes you'll hear people describe the end behavior of a function. That's what we're talking about as x approaches plus or minus infinity. So, cool. So we're going to talk about doing this in three different ways. Not because you have to do it in three different ways, but because it's good to have more tools in your toolbox when you're thinking about how to consider things. In all likelihood, if you see a question like this, it's going to be a single multiple choice or a single small, probably 1 point part of a free response on your AP exam. Which is one of the reasons why I don't really care how you logic your way through this, as long as you're able to logic your way through this. So here are the three ways that we're going to address this. Number one, I'm going to delve into some prior knowledge that we have from Algebra 2. If you had me for Algebra 2, it would be from section 8.2 in your Algebra 2 book, just like the vertical asymptotes were in the last video. The second way we're going to talk about doing it is using the fact that the limit as x approaches positive or negative infinity of a number on top of an x is 0, which is going to be the method the textbook uses. And then the third method we're going to talk about is just sort of logicking through stuff that has infinities involved. And the logic that some infinities are in fact larger than others. So that's kind of where we're going to start. So yeah, so that's the plan. So let's start with talking about previous knowledge from Algebra 2. So in section 8.2 of Algebra 2, which was probably sometime in early January of last year, if you had me for Algebra 2. So in section 8.2, we learned that rational functions, like a polynomial on top of a polynomial, have horizontal asymptotes depending on the degrees of the numerator and denominator polynomials. So here I used n of x for the numerator polynomial and d of x for the denominator polynomial, and then little n for the degree of that n of x and little d for the degree of that d of x. So there are basically three possibilities, and we're going to ignore the slant asymptote possibility, not because it doesn't exist, but because for our purposes, with limits as x approaches plus or minus infinity, it doesn't really matter to us if a graph has a slant asymptote. So possibility number one, the numerator has a smaller degree than the denominator. So if that happens, if the numerator degree is smaller than the denominator, then the horizontal asymptote in both directions is y equals 0. So if that happens, the limit as x approaches plus or minus infinity of that n of x on top of d of x is 0. Here's an example. If my numerator is 2x plus 3 and my denominator is x squared minus 7x, you can see the degree of the numerator is a 1, right? The degree of the numerator is a 1. The degree of the denominator is a 2. The numerator degree is smaller. So as x approaches either positive or negative infinity, the output is going to be a 0. Okay? So if you already know that from Algebra 2, if that's something that's already in your toolbox that you have memorized and you feel comfortable with, well, that's great, because it saves you a little bit of work sometimes. The second option is if n and d are the same number. So if the degrees are the same number. So in this second little snippet, I have both of these have squareds as their degrees, right? If that's the case, then your y value of your horizontal asymptote would be the fraction of the leading coefficients. So in this case, that would be a 4 over 5, right? Because the leading coefficients in front of the squareds are a 4 and a 5. So if I wanted to evaluate this limit, knowing my information from Algebra 2, I could just look at it with my eyeballs and say, hey, that's a 4/5 and be done with it, which is awesome and very convenient. Again, if you don't have this prior knowledge, I'm going to give you another way to do this in a little bit, but I would point out that this is knowledge that's kind of helpful. And again, the difference is that if you have to do it using this method that the book's going to advocate, it's absolutely fine, but the amount of time it might take you to do this example might be a minute versus the 5 seconds it takes me based on my prior knowledge, right? So at some point, we want to accrue prior knowledge because it makes us faster and makes us able to do simple problems quickly. Not that there's not another way to do the problems, it's just a lot faster if you have that knowledge. The third possibility is the numerator degree is higher than the denominator, and if that happens, there is no horizontal asymptote. What that means is that the graph is going to go up or down forever, either to positive infinity forever or negative infinity forever. So the easiest thing to do is you know ahead of time that the answer is going to be an infinity. It's either positive or negative. Pick a number that's fairly big, right? If you're going to infinity, like this example is, you'd pick a big positive number. And honestly, by big positive number, you could probably pick something like 10. It doesn't even have to be really big. Or if I were going to a negative infinity, I'd pick a negative number. So here I picked 100, because 100 is a big number, but it is also an easy number, right? So when I plug in 100, I got negative 300,000 plus 5, which is a pain, but I don't really care. I'll show you why in a sec. Over 100 minus 7. All I care about, I know the answer is either a positive or negative infinity. I'm just using these numbers to figure out whether this answer comes out positive or negative. The top is a very large negative number. The bottom is a 93 that is positive. So I say, oh, negative divided by positive, hey, it's a negative. Look, the answer must be a negative infinity, okay? So that's one way to evaluate these limits. Now, the trick here is that, notice the knowledge I have from Algebra 2 only works if I have a polynomial on top of a polynomial. I will say that this kind of question right here is pretty common on an AP, where it's the same degree and, oh, hey, look, it's just a fraction of the leading coefficients. Kids that happen to know this information get it really fast. Kids that don't might get it right, but might take a lot more time. That said, this particular set of tricks is only useful if you're looking at a polynomial on top of a polynomial. So, which a lot of these questions are going to be, if I'm being entirely brutally honest. Okay, let's talk about the second option for how we can walk through some of these limits. And again, I did pick a positive infinity in all those examples. I didn't have to, it happened to be what my brain did. Okay, so anyway, second option. We discussed a couple videos back. I gave you like a spoiler alert and said, okay, cool, I should mention that if you have a finite number, right, some finite number on top of something infinite, it's always 0, right? So what your textbook does to do a problem like this, so I'm going to walk you through an example. We'll call this example, it wouldn't be example 1, would it? Because we did vertical asymptotes, so it's probably example 2, my bad. Okay, so example 2. We're going to evaluate the limits. So let's do the limit as x approaches infinity of, let's do x plus 3 over x squared minus 7x plus 1. Okay. Now, some of you are probably looking at this. Oh, I'll give you a b, hang on. Let's do the limit as x approaches negative infinity of 2x cubed plus 3x minus 1 over, let's do x cubed minus 6x squared plus 3. Great, cool. Okay, so when you look at this, some of you are looking at this and intuitively able to give me the answer in your head instantly because of your Algebra 2 knowledge. If you can, that's dope. I'm going to tell you right now that looking at this with my Algebra 2 knowledge, I can say that this answer is a 0 because this degree is a 1 and this degree is a 2. Numerator degree is smaller, answer is 0. Similarly, I can say, oh look, these degrees are both 3's, so this answer is a 2 over 1 or just a 2. So I was able to get both of those answers with essentially no work. One of the reasons I mentioned this is often a multiple choice question or a single point on a large free response is because if you have prior knowledge, this can require literally no work, and it's not fair to penalize you for that. Okay, so that's fine. Let's say I didn't know how to do that. Let's walk through how the textbook would advocate you doing this. And there's nothing wrong with doing it either way. I do it this way because it's faster, but if I were asked to do it the way the textbook does it, I can, and you'll be able to as well. So here's the idea. Anytime we have something finite over something infinite, and we evaluate the limit, it approaches 0, right? So it's going to be 0. So here's what we're going to do. The textbook is going to advocate that you look for the highest degree of x, okay? And what you're going to do, so according to the textbook method, here's what you're going to do. The textbook's going to ask you to multiply both the top and bottom of this thing by 1 over x squared and 1 over x squared. Why x squared? Because the largest degree of x is the x squared. All right, so here's what's going to happen when I do that. Okay, so I'm going to take that, the textbook's going to tell me to take the same limit as x approaches infinity and multiply both the top and the bottom by a 1 over x squared. Okay, and again, I picked the x squared because the largest power of x was x squared. And when I do that, I'm going to get that this is the limit as x approaches infinity of an x on top of an x squared plus a 3 on top of an x squared over an x squared on top of an x squared minus a 7x on top of an x squared plus a 1 over an x squared, right? I am going to run a little bit light on space, so I'm going to give myself a little room by erasing this and working my way down, and I'll just fix it in a second. So I'm going to get that this is the limit, if I clean this up a little bit, of a 1 over x, because that's what happened to the x squared over x, plus a 3 over x squared, plus a 1, over a 1 minus a 7 over x plus a 1 over x squared. You with me? Hopefully. I know it's a video, so you can't answer me, my bad. All right, so here's the idea. When I plug in the infinities now, all of these things that have a number on top of an infinity are going to be 0. So when I plug in, I'm going to get 0 plus 0, right? Because it's 1 over infinity, 3 over infinity squared. And then a 1 minus 0 plus 0, that's a 0 over 1, which is totally a 0, right? So all of these values that had a number on top of an x or an x squared or whatever, they all end up being 0, and I get 0. Notice I got 0 intuitively with a little bit of Algebra 2 prior knowledge. Boom, I'm done in under probably 10 seconds. The way to do it with the textbook is going to require a lot more math, a lot more work. Notice I get to the same spot, and I'm not really getting any more credit for this answer than I was getting for this answer. Now, if I asked you to show work on a problem, which again, it's unlikely that you're going to have to do a problem like this on the AP and show work, but if on one of my tests I were to ask you to show work, your work can also be an explanation. It can say numerator degree is a 1, denominator degree is a 2, boom, it's a 0. That's enough explanation, right? Like you could say, hey, look, 1 is smaller than 2, so hey, I get that the horizontal asymptote's a 0. I just need you to communicate the understanding, right? Now, we already talked about how if I were going to do B the fast way, I would say, oh, look, the degrees are 3 and 3, it's the leading coefficients, 2 over 1, boom, it's a 2. Fine. If I were going to do it the longer way, which is the way I just did this, so let me erase and give myself a little bit of space. If I were going to do this the longer way, what I would need to do is multiply. I look and say, oh, look, the biggest power of x is an x cubed. So the longer way to do this is to multiply both the top and bottom by a 1 over x cubed. It does have to be the same thing on the top and bottom, right? Because remember, I'm actually multiplying by 1. That's the thing I'm mathematically allowed to do. So when I clean this up, I'm going to get that this is the limit as x approaches negative infinity of a 2x cubed over an x cubed plus a 3x over an x cubed plus, minus, not that it'll particularly matter, but minus a 1 over an x cubed, all over an x cubed over an x cubed plus, come on brain, minus a 6x squared over an x cubed plus a 3 over an x cubed, right? Now, when I clean this up a little bit more, I'm going to get that this is the limit as x approaches a negative infinity of a 2, because the x cubes would cancel, plus a 3 over an x squared minus a 1 over an x cubed, all over a 1 minus a 6 over an x plus a 3 over an x cubed. Now, when I plug in those infinities, anybody that's a number on top of an infinity is going to be 0. So when I plug in, I'm going to get that this thing, here we'll come up here to do it, when I plug in, I'm going to get 2 plus 0 minus 0 over 1 minus 0 plus 0. Oh, look, that's a 2 over 1, which is a 2, which is the same answer I got intuitively, right? And actually, I shouldn't say intuitively. It's the same answer I got using my Algebra 2 previous knowledge, okay? So let's do a P2, which is similar. I'm going to give you one. Again, I don't actually care which of these two options you pick. It doesn't matter to me whether you pick using the Algebra 2 knowledge or whether you pick doing it the slightly longer way that the textbook does. I don't care. So limit as x approaches negative infinity. Let's do a 4x minus 3 over x squared plus 8. And for B, let's do the limit as x approaches infinity of a 10x squared minus 3x over a 2x squared plus 8. Great. All right, cool. I don't know why I picked 8 of both. Okay, so if you want to pause me, this would be a good time to do it. So for both of these, I'm gonna go ahead and do the short way first and just tell you, hey, I can spot the answer and here's why. Remember, if you were trying to show work on a problem like that, you just have to communicate how you were able to make that mental leap. So short version of this problem, I say, oh look, 1 is smaller than 2, the numerator degree is smaller than the denominator, the answer to this is 0. Great. So again, all I'd have to do is communicate that in some way. It doesn't have to be beautiful full sentences, you just have to communicate in some way. Okay, cool, that's what I did. Here, I see that the degrees are the same, so I know that it's a fraction of the leading coefficients. It would be 10 halves or 5, right? So 5 or 10 halves. Now, that's great. If you don't see the shortcut, or if you wanted to do it the slightly longer way, the other way to do this is to recognize that what I'm going to do is take the largest power of x that I see, which in this case is an x squared, and multiply by 1 over x squared times 1 over x squared, right? So that would give me, if I were to multiply this, so to times the whole thing by that, right, I would get a 4x over x squared minus a 3 over x squared over an x squared over x squared plus an 8 over x squared, which would be the limit as x approaches negative infinity of 4 minus 3 over x squared over 4 over x, my bad, come on brain, plus 8 over x squared, right? And then if I plug in, I'd get 0 minus 0 over 1 plus 0, which is totally a 0 over 1. Oh look, it's a 0, which is the same answer we got using prior knowledge, right? Again, it's not cheating to know more than other people, right? Having prior knowledge that makes you do problems faster is not wrong, it's awesome. It doesn't mean that you can memorize everything that you've ever heard, but it does mean that when you start to find certain things are useful, you should commit them to memory and use them, because being faster and right is better than being slow and right. Right is the important part there, but if you can speed up stuff by knowing stuff, it's awesome. All right, so same thing here. I see that the biggest power is an x squared in both the top and the bottom, so what I'm going to do is I'm going to multiply by 1 over x squared on both the top and the bottom. So 10x squared minus 3x, the whole thing will be times by a 1 over x squared, and 2x squared plus 8, the whole thing is going to be multiplied by a 1 over x squared. So when I do that, and again, if you can skip the step where you simplify a little bit, the 10x squared over x squared is just going to be a 10 minus a 3 over an x, because one of those x's will cancel. I'm going to get a 2 plus an 8 over x squared. Now when I go to plug in, both of these guys are going to get knocked out because they are a number that is finite over something that is infinite. So I'm going to get 10 minus 0 over 2 minus 0, 2 plus 0, not that it matters, which is 10 halves, or totally a 5. Again, not cheating if you're able to spot that using previous knowledge. Okay, cool. So let's stop this one here, and in our next video, what we'll do is we'll talk about the ones that go to infinite values, and then we'll talk about using some logic with infinities.